Hello, and welcome back to the course on classical electromagnetism. So we are now on the fourth lesson for this chapter. So before we proceed, let us review some concepts. So we have discussed about Faraday's law in the previous lessons, which describes the induced EMF in a conducting loop due to a changing magnetic flux or changing magnetic flux, which can be due to a changing magnetic field or a changing area of the conducting loop. So here you see that the magnetic flux is the integral of B dot dA. So in this lesson, we will be talking about inductance, specifically the two types, the mutual inductance, the mutually induced EMF between two conducting loops, and self-inductance, the self-induced EMF of a conducting loop. So let's first start with mutual inductance. So this is the mutually induced EMFs between two conducting loops or two current loops. So suppose you have two conducting loops carrying currents I1 and I2, and they have differential, this is just the differential length, DL1 and DL2. So there will be a flux on loop number 1 due to loop number 2. So if the magnetic field of loop number 2 is changing, then this will induce a flux on loop number 1. So the flux on loop number 1 is just integral of magnetic field of loop number 2 dot dA1. Sorry. So the magnetic field on loop number 1 is just the magnetic field of loop number 2 dot the area of loop number 1. Similarly, loop 1 will induce a flux on loop number 2. It's equal to the flux on loop 2 is now B1 dot dA2. The magnetic field of loop number 1 on the area of loop number 2. So these two magnetic flux are actually related. So by this quantity called M. So we can actually write the flux on loop number 1 as M times I2, where I2 is the loop in current 2. And similarly, the flux in loop 2 is just M times the current in loop number 1. And we call this M as the mutual inductance. And therefore, the induced EMF in loop number 2 is just a change in flux in loop 2, which is just due to the changing current in 1. And the induced EMF in loop number 1 is due to the changing current of loop number 2. They have the same proportionality constant M, which is what we call the mutual inductance. So the mutual inductance is not dependent on the magnetic field, strength of the magnetic field, or the current. Similar with capacitance, similar with resistance, it only depends on the geometry or the shape, or similar to the capacitance, it depends only on the geometry, shape or the size of the loops or the material. Okay. So another type of inductance is what we call self-inductance, and basically this is the induction of a loop on itself. So if, say for example, the flux on the loop or the magnetic field produced by the loop is changing, then that will induce a magnetic field and electric field on itself, on the loop. And basically, when we say inductance, we mean self-inductance. So when we just plainly say inductance, we usually refer to just to self-inductance, and its symbol is L. So mutual inductance is M, inductance or self-inductance or just inductance is L. So suppose you have a loop and you have a time varying current in your loop, then there will be a flux on your loop equal to the inductance L times the current. Take note, for the mutual inductance, it's M times the current of the other loop, but here it's just, there's no other loop here, so it's just the inductance times its own current, L times I. And the induced EMF, or the self-induced EMF, is just negative L di dt. Now, if you will recall, in the mutual inductance, it's M, the current of the other loop, dt. Okay. So basically, self-inductance or inductance in general is just a measure of how much a material resists changes in magnetic flux. So if you have a large inductance, meaning it has a large resistance to changes in magnetic flux. So an inductor is basically a material with specific inductance. So examples are, you have the ballast in your fluorescent lamps or bulbs, a spark plug, that is an inductor. So the symbol for inductor is basically a coil. So its symbol is, circuit symbol is a coil. Its name symbol is the letter L. Okay. So we need to be careful with our length here because it's also L. Okay. Okay, so length our symbol for length now is small l. So we have a short solenoid, so this one, of length L and radius A, with NA turns per length. This is the number of turns per unit length. It lies on the axis of a very long solenoid. So there's a second solenoid, a very long solenoid, with radius B and NB turns per length. Current I flows in the short solenoid. So what is the flux through the long solenoid? Okay, so this is a problem for mutual inductance. There are two loops or two coils here. Okay. So we are asked to find the flux in the long solenoid due to the magnetic field of the short solenoid. So we have phi B, the flux on B, small, I'm just going to use small b. And that's actually equal to the mutual inductance of the two loops times the current in loop A, which is I, the short solenoid. So the short solenoid is A, the long solenoid is B. So Mi. So we need to solve for M here, the mutual inductance first, before we can solve this problem. Now, the flux through A is also similar. It's M times the current in loop number in the long solenoid. So we can actually solve this problem by doing the reverse, so that we can solve for the mutual inductance. We can actually solve for, instead of putting the current I in the short solenoid, take note, this is also equal to the integral of the magnetic field of A, that the area of B. That's our definition for the flux on B, the long solenoid, is the magnetic field of A, the short solenoid, that with the area of cross-sectional area of B. Now, the problem is, this is a short solenoid. Inside the solenoid, the magnetic field is uniform, but outside the solenoid, it's already non-uniform. So it's hard to solve for BA. But if we take the reverse, instead, find the flux on A and let the current flow through the long solenoid, which is B, then this is just equal to magnetic field of B. So the flux on A is just the magnetic field on B, that the area of A, that one. So this is basically just the magnetic field of B. We know that the magnetic field of a solenoid is mu naught. So basically this will just reduce to the magnetic field of B times the area of A. So we will assume that B and dA are in the same direction, and B doesn't depend on the area, so you can take it out of the integral and you will have B times area, magnetic field times area. So the magnetic field of B inside is uniform. So we have solved that the magnetic field of a solenoid is actually mu naught NB times I, assuming that the current I flows through the long solenoid. And the area of the small cross-sectional area of the short solenoid, its radius is A, So it's the area is pi a squared. This is only, but this flux is only for a single loop. In order to get the flux on all of the loops in the short solenoid, we need to multiply it by its number of turns. So in this case, its number of turns is just its number of turns per unit length times the length of solenoid A, NA over LA. So NA over LA will give you the number of turns. So this is number per unit length times length, you will get the number of turns. So this will give you the total. So this should be NA, the number of turns in A. This should be in the formula here. There should be a number of turns in A, and this should be, because we need to multiply B dot dA with how many number of turns, because B dot dA is only for a single loop. So you need to multiply by the number of turns for loop A, small a. This is small a. And the number of turns is just the number of turns per length times the length. Okay. Okay. So here we have Mi is equal to mu naught Na LA. Sorry, the length of the short solenoid is L, so we no longer need to put the subscript A here. So the long solenoid is very long, so we don't know its length. We don't actually need its length. So the short solenoid has actually a length L. Okay, so mu naught Na, I will just put NB here, mu naught Na NB L pi a squared times I. And from this, mu naught pi a squared Na NB L. So from this comparison, we see that this is just our mutual inductance, M times I. So we know our mutual inductance. We can now solve for the flux on B, loop B, assuming the current is in loop A. So it's just the mutual inductance, mu naught Na NB L pi a squared times the current phi. So they have the same mutual, they have the same flux in this case. So as a summary, this is the flux in loop B due to the current in the short solenoid. Okay, so let's now have an example on inductance. So we have a toroidal solenoid with a rectangular cross-sectional area. So find the inductance of this solenoid carrying N turns. So in this, in your basic electromagnetism, you have obtained the magnetic field of a toroidal solenoid. It's just equal to mu naught Ni over 2 pi S P hat. So this is the magnetic field inside here, inside the toroid, inside the toroid. It's equal to mu naught Ni over 2 pi S. Actually, the magnetic field is 0 in the space here and outside of the toroid. But inside the toroid, you get this magnetic field. So N is the number of turns, I is the current flowing, S is the distance from the center of the toroid, and the direction is P hat. Okay. Okay. So we're asked to find the inductance. So one way to solve this, if you will notice, you can find the inductance if you know the flux. The flux on a self-induction is L times I. So if we know the flux, since we already know the current I, then we can solve for L. So the flux in this case is just the number of turns times integral of B dot dA. Again, we need to multiply by the number of turns if we now have more than one loop that is being induced. So there are n loops here, and these n loops are actually inducing on its own n number of loops. So you have n. NB dot N flux. So we have N, and then you will have the magnetic field is mu naught Ni over 2 pi S P hat. Our dA here, the area vector perpendicular to this cross-sectional area is also in the same direction as the magnetic field. It's also P hat. In this case, our dA has it's a rectangle, so its height is h, its width is this is basically ds. This is the ds axis, ds. So ds will actually be evaluated from A to B. This direction is P hat. So ds is from A to B. So you simplify and you will get you have ds over s. You will get ln of s, and then evaluated from A to B. So you will get a final value of mu naught n squared h over 2 pi ln of B over A times I. This is equal to L times I, so meaning this is the value of your inductance, L times I. Okay, similar with what we did in the mutual inductance example. Okay, so this is the mutual inductance of this toroidal solenoid. For our last example, we will analyze in a resistor inductor circuit, or an RL circuit. So the RL circuit is connected to a source of EMF, say a battery, with EMF sub-zero or EMF naught. So we are asked to find then the current as a function of time when the switch in an RL circuit is closed. So take note, originally the current is 0 because the switch is open. But when you switch the current on, the current or the switch is closed, the current will actually surge from a 0 value to an increasing value. So the current will surge, the current will increase. But the purpose of the inductor is to regulate the current. The purpose of an inductor in a circuit is to control the flow of current, because again, nature doesn't want any changes in flux. It doesn't want any changes in current. It only wants a constant current. So an inductor produces that one. That's the purpose of the inductor, to regulate the current. So since the current is surging or increasing, the inductor will actually there will be an induced EMF in the inductor that will oppose the change in or surge in current until such time that the current will now become steady state. So it will now become a steady state current. It will no longer change rapidly. Okay, so usually inductors are very sensitive to high frequency current. So if you have a slow varying current, that's okay for inductors. But if you have a fast varying current, inductors will react very sensitively to fast varying current. So we will assume that this is a fast varying current because from 0, the current will surge. Okay, so we asked to find the current. So it's actually time dependent in this case. So we start with Ohm's law. V is equal to I times R. So the total voltage in the circuit is just the voltage of the source plus the induced EMF in the inductor, and that's equal to the voltage delivered to the resistor. Voltage of the source to then a voltage delivered to the resistor. So basically, your inductor is basically similar to a capacitor. It stores potential energy. But in the case of inductors, it stores magnetic potential energy. Okay, so we have epsilon naught, and the induced EMF is just negative L di dt. This is I times R. So we have L di dt is equal to the EMF minus IR. We change variable. So we let say EMF prime equal to EMF naught minus IR. So meaning the differential of this is just equal to negative R di. So meaning di is just dE prime over negative dE prime over R. So I can change dI here with negative d EMF prime over R. So this equation will now become negative L over R d EMF prime dt, and it's equal to EMF prime. So this is now a simple integral. E prime over E prime is equal to negative R over L dt. You integrate this one, say from 0 to t, and this is, say, from an initial value. When the initial value is when the circuit is open, so current is 0. In that case, when current is 0, the EMF is E naught. But when the circuit is now closed, the EMF prime is now E naught minus IR. So this is E naught minus IR. Okay. So you simplify all of that, and you will get, you can solve for I, and you will get I equal to this value. So I will just let you continue this one. This is just very easy integral. So I here is this one. So you will notice that at time is equal to 0, e to the 0 is 1, so you have 1 minus 1, 0, so the current is 0 at the start. And at a later time, say at time approaches infinity, you will have e to the negative infinity, which is 0. So E naught over R is the final value of the current, when the current no longer increases. So if you plot this one, plot the current with respect to time, it will have something like this. So it will surge, but there will come a time that it will now plateau. But there's a certain time where the current plateaus. So just like the COVID cases flatten the curve. The curve flattens after a certain amount of time. Okay. So that is the end of this lesson. For our next lesson, we will be focusing on the energy stored in inductors, which is basically magnetic potential energy. And similar to capacitors, the energy stored in inductors are stored within the magnetic field. So I will see you again in the next lesson.